Hi, in previous lecture I discussed asymptotic notations including big and small like big O, big omega, theta, little o and little omega. Let's discuss some examples. First example, f of n equals to 2 power 100. We can write O of 1 or omega of 1 or theta of 1. Maximum time we use the big notation. And for any constant, we can write O of 1, omega of 1 or theta of 1. That constant may be a big number or a small number. Like for 8 power 10000, for how big number you can write it as order of 1. Let's see second function 2 power 100 plus log n. For this we can write order of 1. For log n we can write order of log n. This function is an addition of a constant and a logarithm. Now from these two, what is maximum that we consider? So maximum is log n. We can write O of log n or omega of log n or theta of log n. When one function is addition of two functions, then maximum function running time will be running time for that whole function. So log n running time will be running time for this function. Let's see another example 2n plus 1000. For this running time will be order of n and for 1000 it will be order of 1. Now maximum from these two will be order of n. So you can write O of n or omega of n or theta of n. Let's see another example n square plus log n. This we can write O of n square and log n we can write O of log n. Now addition of these two, so we'll consider what is maximum. Maximum is n square. So running time will be either O of n square or omega of n square or theta of n square. Sum of I equals to 1 to n 1. We can simplify this as 1 plus 1 plus 1 n time. So addition will be n. We can write O of n or omega of n or theta of n. Next function I equals to 1 to n I. We can simplify this as 1 plus 2 plus 3 up to n. And for this we know the formula, it is n into n plus 1 by 2. After simplification you will get n square plus n by 2. That again you can simplify n square by 2 plus n by 2. For this running time will be O of n square and for n by 2 running time will be order of n. Now it is addition of these two, so what is maximum that will consider as a running time? Maximum is n square, so it will be O of n square or omega of n square or theta of n square. Next example, sum of I equals to 1 to n I square. We can simplify this as 1 square plus 2 square plus 3 square up to n square. And for this we know the formula that it is n into n plus 1 into 2n plus 1 by 6. If we simplify this term, you will get some constant multiplied by n power 3. So we can write running time as O of n power 3 or omega of n power 3 or theta of n power 3. When it will be I cube, I power 3, we can write O of n power 4, power plus 1. When it is sum I power 4, we can write O of n power 5. When it is sum of I power 10, we can write O of n power 11. Let's see next example. Sum of I equals to 1 to n log I. You can simplify this as log 1 plus log 2 up to log n. And again this you can simplify log 1 multiplication 2 multiplication 3 up to n. And this thing you can write as n factorial. And for n factorial, upper bound will be n power n. You can write this as O of log n power n. Then this n you can take to left side, so you can simplify as O of n log n. As minimum it can be log 1. If we will take lower bound for all these numbers, so 1 multiplication 1 multiplication 1, it will be log 1. So 2 power 0, that will be log 1. It will be 0 and that will be the lower bound. And in running time, we always write positive function or positive number, not 0. Let's see next function. Sum of I equals to 1 to n, 1 divided 2 per I. That you can simplify was 1 divided 2 plus 1 divided 2 per 2 plus 1 divided 2 per 3 up to 1 divided 2 per n. Now what is the value of this? This value you can write as 1 minus 1 by 2 per n. So maximum will be 1. So this function we can write as O of 1. Its upper bound will be 1. Let's see another function, n factorial. N factorial you can write as 1 multiplication 2 multiplication 3 up to multiplication n. Now if we take lower bound and upper bound, lower bound in place of every number we can write 1, upper bound in place of every number we can write n. So you can write 1 multiplication up to n time 1 multiplication, that will be less than equals to n factorial, that will be less than equals to n multiplied n time. So you can write 1 will be less than equals to n factorial will be less than equals to n power n. So for n factorial, we can write omega of 1 or O of n power n. This is the upper bound while 1 is the lower bound. And there is no tight bound for n factorial. Let's see next example, log n factorial. For this n factorial, upper bound will be n power n. So you can write O of log n power n. Next, this power n you can take to left side, so you can write O of n log n. For this there is no theta and there is no omega. We can consider lower bound for n factorial as 1. So log of 1, log of 1 will be what? It will be 0. 2 power 0 will be 1, so it will be 0. And we cannot write omega of 0 as minimum is constant, minimum is 1. So cannot write omega of 0. That's why we can only write O of n log n. There is no theta and there is no omega. There is just upper bound, no tight bound and no lower bound. Let's check some asymptotic relation, either it is true or false. First, 100 n log n equals to O of n log n. This is true. Any constant multiplied by n log n, we can write O of n log n. Next, root of log n equals to O of log n. This is false. Root of log n, that you can write as log n power 1 by 2. This is polylogarithm, and log of log n, that is double logarithm. And we already know that log of log n is less than log n power 1 by 2. So this is false. We can write log of log n equals to order of root log n. I already discussed how we can compare two functions. You can compare two functions by putting some number or by limit function, or you can take log in both sides or by just order of growth sequence. Next relation, 1 by n equals to O of log n. This is true. 1 by n, that value will be less than equals to 1, that value will be less than equals to log n. So you can say for 1 divide n, upper bound can be log of n. Next, 2 power n plus 1 equals to O of 2 power n. This is true. This we can simplify as 2 power n multiplication 2. This is a constant, so we can write O of 2 power n. Next function, 2 power 2n equals to O of 2 power n. 2 power 2n, or that you can write as 2 power 2 power n, that you can simplify as 4 power n. 4 power n is greater than 2 power n, so this is false. Next function, 0 less than x less than y, then you can write n power x equals to O of n power y. This is true. Suppose x is 1 less than 2, then we can write n less than n square, or we can write n equals to order of n square. Next, n plus k power m equals to O of n power m for m and k greater than 0. This is true. Let me simplify. Let me write n plus 3 power 2. This 3 is for k, this 2 is for m. We know what is formula for a plus b whole square. We can write a square plus b square, that will be 9, plus 2ab, that will be 6n. Now for this, turning time will be O of n square. For this, O of 1. For this, O of n. Now maximum from this is n square, so we can write order of n square. So we can generalize it. For n plus k power m, we can write O of n power m. Even we can write theta of n power m or omega of n power m. 2 power n power 2 equals to O of n. This is wrong. This is polynomial while this is exponential. So 2 power n power 2 have higher order of growth than n. We can write n equals to O of 2 power n power 2. Next function, sum of I equals to 1 to n divide I. This is true. This summation you can simplify as n by 1 plus n by 2 plus n by 3 up to n by n, and you can take n as a common, so n 1 by 1 plus 1 by 2 plus up to 1 by n, and this value is log n, and before there is a n, so this n log n we can write O of n log n. Suppose Fn equals to n, Gn equals to n square, then we can write Fn equal to O of Gn, as n square have higher order of growth than n, and we can write Gn equals to omega of Fn. Next, suppose Fn equals to 2 power 10,000 and Gn equals to log n. This is a constant and this is a logarithm. Constant have lower order of growth than logarithm. So you can write Fn equals to O of Gn or Gn equals to omega of Fn. Fn value is lower than Gn value and Gn value is greater than Fn value. Next, suppose Fn equals to 2 power n and Gn equals to n square. 2 power n is exponential, n square is polynomial. Exponential have higher order of growth than polynomial. So we can write Gn equals to O of Fn. Means we can write n square equals to O of 2 power n. 2 power n have higher order of growth than n square. Or we can write Fn equals to omega of Gn. Means we can write 2n equals to omega of n square. I think this much example for asymptotic notation is enough. In next lecture, I will discuss asymptotic notation properties. If this lecture is helpful for you, please like and subscribe. Thank you.